Okay, we're going to switch gears a little bit now and talk about atoms themselves. And so, in the first lecture, we talked a bit about how to classify different types of substances. So, we can classify a substance as pure or a mixture depending on the types of particles it has. Or we could classify a change as physical or chemical depending on what's happening to those particles. But we haven't actually talked a lot about the particles themselves. And so now we're going to kind of dive a little bit deeper into what these atoms actually are. And so first we're just going to start by talking about how small they are, which is pretty small. So to get an idea of how small atoms are, imagine this: if every atom within one small pebble were the size of the pebble itself, the pebble would be larger than Mount Everest. So that's just to say that these atoms are so incredibly tiny that when you pick up one single grain of sand, a single grain of sand has a trillion atoms in it. A single grain of sand that's so small that you can't even see has more atoms in it than you'll ever be able to count in your entire life. So that's how small they are. Really, 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 really small. And even when we consider how small they are, it's even more perplexing to think that they're actually mostly empty space. So there is, in the center of every atom is what we call the nucleus. And the nucleus is where most of the atom's mass is, and all of its positively charged protons. So protons are positively charged particles, and they're in the nucleus. Neutrons are neutral particles, and they're also in the nucleus. So protons and neutrons make up the nucleus. The nucleus has most of the mass in the whole atom, and it is positively charged because protons are positive and neutrons are neutral, which means they don't affect the charge. Most of the volume is empty space around the atom, and in that mostly empty space, there are teeny tiny particles called electrons. And electrons are negatively charged, and they occupy that space outside of the nucleus. So, in general, most atoms are usually neutral, which is to say that there's some number of positive protons. In this atom that we see on the screen, there's three red protons. That means that there is a positive charge of 3 plus 3, and there are also 3 electrons in this atom, and each electron has a negative charge. So that means there's a negative charge of -3. So plus 3 and -3 cancel each other out to equal a total charge of 0. So this atom that we're seeing on the screen has a charge of 0. Because remember, even though there's 3 neutrons, those neutrons have no charge. So their charge is equal to 0 already. Another thing that we have to understand about charges themselves is what happens to charges when they interact. And you're probably familiar with this from playing with magnets. If you've ever played with a bar magnet when you were a kid, and you know that a magnet has 2 ends that are different than each other. And if you point the 2 ends of the magnet towards each other, of 2 different magnets, if you point their opposite ends toward each other, then they'll be sticky. They'll attract. The positive side and the negative side, or the north end of the magnet and the south end of the magnet, will attract each other. However, if you put the north end and the north end of the magnet toward each other, or the plus end and the plus end, you will feel that they repel each other. You'll feel them pushing away. Same with the negative end and the negative end. They will also repel. So what we can see here is that charges that are not the same, a positive charge and a negative charge, are attracted to each other. But charges that are the same, a positive charge and a positive, or a negative charge and a negative, they push away. They repel each other. And finally, when we have one positive and one negative, when they hang out right next to each other, their charges cancel, and so they have a total charge of 0 at that point. So this is just kind of a summary table about what we've just said. Protons and neutrons have more mass than electrons. They're much bigger. We can see this number here. Protons and neutrons have almost the same amount of mass, 1.67, and then a few other numbers, times 10 to the negative 27 kilograms. And electrons are also times 10 to the negative 27 kilograms, but that number at the beginning is much smaller. So that's just to say that the mass of a proton and a neutron is much bigger than the mass of an electron. And also that the mass of a proton and a neutron is almost equal. They're almost the same, but not quite. Also, their charge is different for each of these particles. A proton has a +1 charge, a neutron has a 0 charge, and an electron has a -1 charge. And we can also represent that charge using different units. For example, the coulomb, that's what that C is, charge, and then the C in parentheses. That's just another unit that we can use to measure charge, in the same way that we can use different units to measure mass. So when we look at the periodic table, the first thing that we notice is that there's lots of different elements. There's hydrogen and helium and lithium and so on, lots of different elements. What makes an element different? Why is hydrogen different than helium? Why is helium different than lithium? Well, remember all of the atoms on the periodic table. They're all made of the same three things: proton, neutron, electron. There's only three things in all of those different elements. So what makes them different than each other is the number of particles that they have. And specifically, when we're talking about why hydrogen is not the same as helium, and why helium is not the same as gold, the specific particle that makes elements different is protons. If we have one proton, it doesn't matter how many of the other particles we have. Every particle that has one proton is hydrogen. Every particle that has two protons is helium. It doesn't matter if it has 0 neutrons or 1 neutron or 2 neutrons or 0 electrons. It can have any number of neutrons potentially or any number of electrons potentially, but as long as it has 2 protons, it's always helium. And that's why we say that the atomic number is the number that defines what kind of atom we have. It tells us what type of element that atom is. And the only number that we need is how many protons there are. If we can look at a nucleus and count the number of protons, then we know what element we're looking at, regardless of how many neutrons, regardless of how many electrons. And those can change, those numbers can change. So elements are defined by their number of protons. If an atom had a different number of protons, it would be a different element. The number of protons in the nucleus is called the atomic number, and it's given by the symbol Z. So here's the periodic table. We can see that all of these elements are separated with their different symbols: H, He, Li, Be, and so on. Those are the chemical symbols. And they're also organized according to that number on the top. That number on the top is called the atomic number, Z. And it's handy when we look at the periodic table. We can see that it just counts from left to right: 1, 2, 3, 4, 5, 6, 7, 8, 9. And without knowing more, you might think, oh, well, that's just the number of the element, because they just go in order. So that's carbon is the 6th element. Well, that 6, it is the 6th element, but that 6 also has greater significance. It tells us that there are 6 protons in the nucleus. And nitrogen next door has 7 protons in the nucleus. And so that number is actually telling us how many protons there are. So we can look at the number at the top of any of these boxes, and that number is the number of protons. How many protons are in MO? 42. How many protons are in K? 19. It's just that number on top. And so that number is handy because it also helps us organize the periodic table in order: 1, 2, 3, 4, 5, 6, 7, and so on. The atomic mass, that's the number on the bottom. That one's a little tricky, and we're going to talk about how we can understand what that number means. But at this point, let's just say it's the number of protons and neutrons. So if beryllium, we can see on the screen there, has an atomic mass of 9.01, let's just say its atomic mass is 9. That means that it has 4 protons, and we know that because the 4 is on top. The atomic number tells us how many protons, and the atomic mass says there's 9 protons and neutrons all together, and if 4 of them are protons, then the other 5 must be neutrons. So the mass is really just protons plus neutrons. Remember, we said protons and neutrons are much bigger than electrons. They have much more mass. So when we consider the atomic mass of an element, we're only considering the protons and neutrons. We don't really care how many electrons it has. Now, why is it say 9.01? That's a bit more complex than what I've said here, and we will get to that later. Okay, another thing we can see on the periodic table. We can classify an element as to whether it is a metal, a non-metal, or a metalloid, or sometimes called a semi-metal. Not quite a metal, not quite a non-metal, in the middle. So there's this dark, bold, black zigzag line that you can see that starts at B, and it kind of zigzags down to SI, and it kind of zigzags down to AS, and you kind of see this ladder, this kind of dark black ladder on the right side of the periodic table. That dark black zigzag ladder separates the metals from the non-metals. The non-metals are on the right, those are the green ones, and the metals are on the left, those are the tan ones. And the semi-metals, the metalloids, those are the ones that sit right on the line, and those are kind of not quite metals and not quite metalloids. And you can see from this picture, all of the metalloids follow a pretty good pattern except for aluminum. Al seems like it should be a metalloid because of where it is, but it's not. Aluminum is a metal. Aluminum cans, you're familiar with aluminum, you're familiar with the metal aluminum. It's not a metalloid, it's a metal. So it's in kind of a strange position there on the table where it seems like it should be a semi-metal or a metalloid, but it's not. But all the others that are touching that line are the purple ones. Those are the metalloids. They have some properties of metals, and they have some properties of nonmetals. Now, metals and nonmetals are quite different. Metals are solid, and they're shiny, generally, and they conduct electricity. On the other side, the nonmetals, those green things, those are usually like gases, oxygen, nitrogen. Carbon is a diamond when it's pure. We have helium and neon and argon, the noble gases. Fluorine and chlorine and bromine, they're kind of like gases and liquids, and they're very much different than solid, shiny metals. So non-metals and metals are quite different than each other. And those metalloids in the middle are kind of in the middle. They kind of have properties of both types of element. Notice one more thing. On the left, we have H. H is technically on the left side of that zigzag staircase. So that would make it, by that rule, it would make it a metal. But hydrogen is not a metal. We know that hydrogen is a gas. Hydrogen is a flammable gas. And so, being that hydrogen is a gas, it's most certainly not a metal. And so hydrogen belongs with the nonmetals. So hydrogen is also in kind of a funny place on the periodic table, in that it kind of doesn't follow all of the same rules. So if I ask you if hydrogen is a metal or a nonmetal, don't get tricked. Just because of its position on the table being there on the left, it's still green. Hydrogen is still a non-metal because it is a gas. We can also further distinguish the elements based on whether they are main group elements, those are the ones in yellow, or transition series elements, those are the ones in blue. So the groups that are yellow, the elements that are in a column, so for example, H doesn't quite count. See how H has that dark line underneath it? That's to symbolize that H isn't really a part of that family that it's in. It's not really like Li and Na and K and all the ones that are below it. So it has a dark line to separate it. But generally, when an element is in a column like that, all the elements that are in a column are usually pretty similar. So lithium, number 3, number 11, and number 19, Li, Na, and K, and Rb and Cs, and all the ones down that whole row, and that whole column, those are all very similar to each other in terms of their properties and how they react. Same with 2A. You see, that's called the group number. So those elements in 1A are similar to each other, but different than the ones in 2A. The ones in 2A are similar to each other, but different than the ones in 1A, and so on. The ones in 3A we can see are similar to each other, the ones in 4A. So when we go down these columns, the elements generally have similar properties to each other. That is more true in the main group elements than it is in the transition elements. So the reason that we have this distinction on this page that we're talking about now, main group versus transition, is because main group elements have predictable properties and they kind of have a pattern. Li reacts with water a little bit, Na reacts with water a little bit more, K reacts with water a little bit more, Rb reacts with water a little bit more. So they're predictable in the way that what they're going to do, right? They're always going to react with water, and their reactivity increases as we go down the series. That's being predictable. They're following a pattern. The ones that are in blue, the transition elements, they are less predictable. Being in a family doesn't mean quite as much for the ones that are in a transition series as it does for the ones that are in the main group. So enough said about that. We're not really going to get into it more than to say is this distinction, and when you look at the periodic table, you'll see 1A, 2A, and then we skip all the blue ones, and then we go 3A, 4A, 5A, and so on. And then if you look at the blue ones, they're B's, 3B, 4B, 5B, 6B, and so on. So the reason that you see these divided into A's and B's is because the ones that are in the A groups are predictable, main group. The ones that are in the B groups, less predictable, transition metals. Okay, now having said that in those columns, elements happen to have similar properties. So like, for example, Li, Na, K, Rb, those are all very similar to each other because they're in the same family, they're in the same column. Those families have names. So that first column, they're called the alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. Now notice that sodium has a chemical formula Na, but its name is sodium. Sodium does not start with an N. So don't get confused by the chemical symbol Na. The reason it has that symbol is because that is the name of that element in Latin is natrium. And so Na are the first two letters of the element in Latin. They're just not the first two letters of the element in English. And K is the same, it has the same kind of situation. K is potassium. There's also a P on the table, which is 15, but 15 is phosphorus. So 19, K, is potassium. So sometimes the chemical symbols do not, the symbol itself does not have the same starting letter as the name of the element. So you have to become familiar with the ones that will trick you. Sodium and potassium are two of the biggest, especially in the healthcare field, because sodium and potassium are very biologically relevant. So don't let that catch you off guard. The next group is called the alkaline earth metals. Those are beryllium, magnesium, calcium, strontium, barium, and radium. Then we skip all those transition metals. The transition metals, some of those families do have names, but that's beyond the scope of this class. And even 3A and 4A and 5A and 6A, those also have names, but we're not going to go over them. But you'll also often hear of the halogens. That's group 7A. So those are fluorine, chlorine, bromine, iodine, and astatine. And finally, group 8A, those are the noble gases: helium, neon, argon, krypton, xenon, and radon. And then down below on the periodic table, we also have these other groups called the lanthanides, and those go from 58 to 71, and the actinides, and those go from 90 to 103. They have a strange place in the periodic table. See how there's kind of a little slice in the periodic table and then an arrow that points to the lanthanides and actinides. You'll see there's a space between La and HF. It goes from 57 to 72. Well, that's because those missing elements, 58 through 71, those are the lanthanides. We just sliced them out and put them down below. And again, it goes from 89 to 104. Those missing elements are the actinides. Those are the ones that are down below. They got sliced out of the periodic table. So the reason that the periodic table is represented this way is because if we actually sliced the periodic table and opened it up and put those elements where they belong, it would be really, really long. And it would be so long, it would be hard for us to print it on a page in a rectangular book. And our books usually have rectangular shapes. So really, this was a change that was made for practicality. We had to kind of slice the lanthanides and actinides out of the periodic table and put them down below so that our periodic table wouldn't be so wide, so long. All right, take a moment, go ahead and pause the video here and see if you can answer these questions. Here are the answers. If you didn't get it quite right, go back and check those slides and see where your miscalculation was. All right, here's another one. Go ahead and pause the video at this point and see if you can get the right answer here. Go ahead. It's okay to look at the periodic table. Okay, here's the number of protons that each of the following elements have. Remember, this is just the atomic number. This is the number that's at the top of the box that each element is in. That number tells you how many protons each atom has. Okay, in chemical reactions, atoms often lose or gain electrons to form charged particles called ions. Positive ions are called cations, and negative ions are called anions. So some examples are magnesium with a superscript 2+, or oxygen with a superscript 2-. And so we've talked about what protons do. If we change the number of protons in an atom, that changes the element. If I have 1 proton, it's hydrogen. If I have 2 protons, it's helium. If I change the number of electrons in an atom, it doesn't change the element. If I have 1 proton and 1 electron, it's hydrogen. If I have 1 proton and 2 electrons, it's still hydrogen. If I have 1 proton and 3 electrons, it's still hydrogen. But if I have 2 protons, now it's not hydrogen anymore. It's only the protons that change the element. So if I change the electrons, what I'm changing is the charge on that atom. So, for example, if H has 1 proton, which is plus, and 1 electron, which is minus, then it has a charge of 0. 1 plus, 1 minus equals 0. But if hydrogen has 1 proton, so 1 plus, and it has 2 electrons, and it has 2 minus, then that means that whole particle has a -1 charge, because 1 proton and 1 electron will cancel out to equal 0. But there were 2 electrons. So if I cancel one of them out, there's still an extra one left over. That extra one still has a negative charge, so it's going to give the whole atom a negative charge. So that would be hydrogen, because it has 1 proton still, but now it has a negative charge, because it has 2 electrons. If I had hydrogen, which has 1 proton, and it had 0 electrons, then it would have a positive charge, because that proton is positive, and there aren't any electrons in the atom to cancel the positive charge. So it would be hydrogen still, because there's 1 proton, and it would have a positive charge, because there aren't any electrons. So depending on how many electrons an atom has, an atom will either have a negative charge, if it has more electrons than protons, a 0 charge if it has exactly the same number of electrons as protons, or a positive charge if there are fewer electrons than protons. So the number of electrons really tells me the charge of the atom. Positively charged atoms are called, well, actually any atom with a charge is called an ion. If it has a positive charge, it's called a cation. If it has a negative charge, it's called an anion. So cation is just positive and anion is negative. Ion is anything that has a charge. So here's a good way for you to remember that cations are positive because cats are good and they make you smile. And also cats have paws, so they're positive. And onions make you cry. Onions are sad. But remember, the word is not onion, so don't let that throw you off. It's anion. It's very similar to onion. So anions are negative, cations are positive. All right, so let's get back to electrons here for a minute. Electrons, we said, go around the nucleus. It's almost like the nucleus is the sun, and the electrons are the planets. It's like an atom is a solar system. And so the electrons are the planets that orbit the sun, and they go on the outside. They can't all go in the same orbit, just like the planets around the sun. The Mercury is the closest. I couldn't remember which one was the closest. Mercury is the closest, and then Venus is a little bit further away, and then Earth is a little bit further away, and then Mars is a little bit further away. So they each are a little bit further away from the center. So electrons are the same way. They're not all equally distant from the nucleus. Some of them are close to the nucleus, and some of them are further away from the nucleus, just like the planets. So we call these shells, just like kind of like an onion too. An onion has layers, and you can kind of like peel the layers of an onion, like the shells of an onion. So an atom is the same way, and the electrons are inside of these shells that go around like the layers of an onion. And so the electrons on the very outside of an atom are called the valence electrons. So the first electron shell can hold 2 electrons. Once it has 2 electrons in it, it's totally full and it can't hold any more. So a helium atom can have 2 electrons in the outside shell. And a lithium atom is the next atom. Helium is atom number 2, element number 2. Lithium is atom number 3. So when I have 2 electrons, they both go in the first shell. But the third electron can't go in that shell because the shell is full when it has 2. Once it has 2, it can't hold any more. So where does the third electron go? It goes in a new shell, further away from the nucleus, outside of that last one. And then we'll start filling up that next shell with the third electron, and the fourth, and the fifth, and the sixth. And that next one can hold 8 electrons, the next shell. Once the second shell has 8 electrons, it gets full too. And then we have to put the 11th electron, because that would be 2 in the first shell, 8 in the second shell. That's 2 plus 8, that's 10. And so where does the 11th go if the first shell is full and the second shell is full? The 11th has to go in the third shell. So these electrons, when we add electrons to an atom, they always go in a shell. And once the shell gets full, we have to start adding electrons into a new shell. And the outermost shell is called the valence shell. So here is what the noble gases look like. The first shell, helium, the first shell can only hold 2. So you see helium has 2 electrons in it, and when it has 2 electrons, it has a full shell. So helium has 1 full shell. Neon has, that first shell is also full. If you look at neon, it kind of looks like helium does, except it has a shell outside of that. So that's to say that neon has 1 full shell in the first shell is also full, and in neon the second shell is also full. Then we go to argon, which has the first shell full, and the second shell full, and the third shell full. And then krypton, first, second, third, fourth. And then xenon, first, second, third, fourth, and fifth. And so as we add more electrons to an atom, each shell can only hold so many electrons before we have to go to a new shell. And so notice that in all of these elements, the first shell can only hold 2. The next shell can only hold 8. So each shell has a specific number of electrons it can hold. The noble gases are special because noble gases have full shells. Their shell is always full. If an atom has a full shell of electrons, then we call it a noble gas. And the noble gases are special in that way because they don't have any chemical reactions. And so that's kind of an interesting thing to think of, that the reason that chemical reactions happen is so that all the other elements that are not noble gases can get a full shell of electrons. That's really the whole reason. All elements want to get a full shell of electrons because a full shell of electrons makes them stable. If they don't have a full shell, they're unstable. But if they do have a full shell, then they're stable and they don't want to do anything. The noble gases here, they all have their outside shell is full. In fact, all of their shells are full. Every shell of electron that's in the noble gases is all full. So that means they don't need to get any more electrons from anybody else. They don't need to give any electrons to anybody else. They are perfectly happy exactly the way they are. They are the most stable elements on the periodic table. So having a full shell of electrons makes an atom stable. Other elements that are not noble gases do not have full shells of electrons. So they will steal electrons from each other, or they'll give electrons to each other, they'll just give them up, or they'll share electrons. They are going to do what they can to trade their electrons with each other so that they can become more stable, so that they can get a full shell of electrons. That's why chemistry happens. That's why chemical bonds happen. Atoms are trading electrons because the electrons want to become more stable. So, that magic number of electrons is usually 8. So that gives us what we call the octet rule, which is that all elements are trying to achieve a full valence shell, which is 8 electrons. To achieve this, they will give up, or steal, or share electrons with their neighbors, except for the noble gases. The noble gases don't have to do any of that because they're already full. So here's the number of valence electrons in each element according to the periodic table. So the periodic table is a pretty neat piece of technology here. We already saw how it counts up from left to right, 1, 2, 3, 4, 5, 6, 7, and it's got that number that goes up in order, which is a really useful way for us to organize anything, to count from left to right and go up in number. But that number also has a dual meaning, which is that it's the number of protons in the nucleus. That's pretty helpful. The other way that the reason that the periodic table has the shape that it has, why are there only 2 elements on the top? And then why are there 8 elements in the next row, and then 8 elements in the next row, and then 18 elements in the next row, and then 18, and then so on and so on? Why does the periodic table have this funny shape that it has? That's because of electrons. The shape that it has is due to the number of valence electrons in the outermost shell. So if we look at the very first row, remember we called those the alkali metals. The alkali metals all have 1 valence electron. Their outermost shell always has 1. This doesn't say anything about their innermost shells. And remember, as atoms get bigger, they always have shells underneath the one that's on the outside. So if we look at all the elements that are in this first column here, they all have 1 electron on the outside, regardless of how many they have on the inside. And they all are going to have a different number of electrons on the inside, because remember, all of these elements also have a different number of protons, because they get bigger and bigger and bigger as we go down the row. So the reason they're in a family, the reason that lithium reacts with water, and sodium reacts with water, and potassium reacts with water, and they all do the same thing, is because they all have 1 valence electron. It's that 1 valence electron that determines the way that they are going to react with other substances. The next group, the alkaline earth metals, have 2 valence electrons. Then we skip the transitions, we skip all the B's, and then we go to 3A. They have 3 valence electrons, and then 4, and then 5, and 6, and 7, and finally we get to the noble gases, and the noble gases have a full shell, which that first shell can only hold 2, and that's why there's only 2 elements in the top row. Hydrogen, 1, helium, 2, that row is done. The reason that that row is done with only 2 elements in the first row is because the first shell can only hold 2 electrons. Then I can ask you, well, how many electrons can the second shell hold? Well, applying that same logic, you would just count the number of elements in the second row. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 elements in the second row. That means the second shell can hold 8 electrons. How many electrons can the third shell hold? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 elements in the third row, so the third shell can hold 8 electrons. So the periodic table is shaped this way based on the number of electrons that are in the valence shell. And notice when we get to the noble gases, that first shell is full at 2, but then all the other shells are full at 8, 8, 8, 8, 8. That's what makes those noble gases so unreactive. They're already full. They already have 8. So when we look at how atoms are going to gain or lose electrons in order to get a full shell, we can start with something like chlorine. If we look at where chlorine is on the periodic table, chlorine is a halogen, which means that it's in that group 7A, and it's right before the noble gases. And that means it has 7 valence electrons. There are 7 electrons in that outermost shell. If we add 1 more electron, then we would get argon. We would get a noble gas. But chlorine doesn't have that last electron. It only has 7 in its outermost shell. But chlorine wants to have 8. So let's look at what happens. Chlorine has 17 protons because it's the 17th element. Its atomic number is 17. And when chlorine is neutral, it also has 17 electrons. 17 protons plus 17 electrons equals 0, a charge of 0. But chlorine doesn't want just 17 electrons, it wants 18. And when it gets 18 electrons, now it has 8 electrons in its outer shell, which makes that outer shell very stable, but it also gives chlorine a negative charge, because I didn't do anything to the number of protons. Chlorine still has 17 protons, but I've added an electron to it. So now there's 17 pluses and 18 minuses. So 1 extra minus is going to give that whole thing a negative charge. So it goes from chlorine neutral to chlorine minus. It goes from a chlorine atom to a chloride ion. So notice that not only did it change from an atom, which is neutral, to an ion, which is charged, and an anion, specifically because this is a negatively charged ion, but the name changed. It went from chlorine to chloride. That's just a way that we name ions, so don't worry too much about it. It's still chlorine, but when it's negatively charged, we call it chloride. And you've probably heard that before, because what do you put on your teeth to make them strong? Fluoride. But the element is fluorine. So when we give a negative charge to fluorine, it becomes fluoride. So that IDE is just telling us that it's an ion. And so this is kind of counterintuitive. Chlorine with 17 protons and 17 electrons is neutral. And intuitively, we think that that means stable because it's symmetric. 17 and 17, it's equal. It has no charge. It's neutral. Neutral is better than plus or minus. So intuitively, we would think a chlorine atom is more stable than a chloride anion. But that's wrong. Chloride ion is actually more stable. Even though it has a negative charge, that negative charge doesn't make it less stable. That negative charge makes it more stable because now it has 8 electrons in its outermost shell, and now its outermost shell is full and it's completely stable. So adding that electron to chlorine actually fills up its outermost shell and makes it kind of look like a noble gas and makes it very stable. And so Cl- minus is more stable than Cl neutral. The same thing with sodium. Sodium, as an atom, has 11 protons and 11 electrons. So it's neutral, it has no charge. But sodium is in that first row. It's an alkali metal. alkali metals have one electron in their outer shell. We would think, okay, well, if sodium has one electron in its outer shell and it wants to be full, it needs to get 7 more because a full shell is 8, right? We just said the octet rule. There's 8. 8 is the magic number. Sodium only has 1. It needs to get 7 more. Well, that's really hard to get 7 electrons. Usually we're dealing with 1 or 2 at a time, definitely not 7 at a time. So sodium has something else it can do. It has, if we remember that there's more than one shell of electrons, right? So sodium has a full first shell. It has 2 electrons in its first shell, and that's full. Sodium also has 8 electrons in its second shell, and the second shell is full too. So 2 plus 8 equals 10 electrons. And then sodium has 1 electron. The 11th electron is in its third shell. So sodium actually has 3 shells of electrons. So to fill up sodium's third shell of electrons, we could give it 7 more electrons. But that would be really hard. Like I just said, we usually only do 1 or 2 at a time, not 7. So sodium could fill up its third shell with 7, or if it gets rid of 1 electron in its third shell, then it has a full shell of electrons underneath, because shell number 2 is full. It has 8, right? Shell number 1 has 2, shell number 2 has 8, and shell number 3, that's the one that has that 1 electron. The 11th electron of sodium is in shell number 3. So instead of gaining 7, sodium really just wants to get rid of 1. So sodium doesn't want to gain any electrons. Chlorine wanted to gain 1. Chlorine gains an electron and becomes Cl-, and it becomes stable. If sodium gains an electron, it's not going to become more stable. It will become maybe closer to a full shell on one side, but further away, if we just can imagine that giving up an electron gets it really close to a full shell underneath. So all of this is to say that sodium gives 1 electron away, so then it has 11 protons and 10 electrons, and that makes it have a positive charge, because now there's more protons than electrons, and now sodium ion has 2 full shells. It has a shell underneath with 2 electrons, and then the second shell has 8 electrons, so that's 10. So it has 2 full shells and a positive charge. So Na plus is more stable than Na neutral, just like Cl minus is more stable than Cl neutral. Now, maybe you see where I'm going with this. You've probably heard of sodium chloride. That's table salt. The salt that we eat is called sodium chloride. When you're worried about your blood pressure, you have to watch how much sodium you eat, right? Well, we're not eating sodium atoms. We're eating sodium ions. Sodium in food is Na plus. And so Na plus wants to get together with Cl minus, because a plus and a minus are like magnets and they stick together. So sodium, when we eat it, sodium in food is always Na plus. It's never Na neutral. And chloride, when we eat it in food, is always Cl minus. It's never Cl neutral. So all of this trading of electrons for chlorine to turn into chloride ion and for sodium atom to turn into sodium ion, that happened a long time ago. And when we find sodium in the environment, it's already Na plus, because that's the most stable form of sodium. When we find chlorine in the environment, it's already Cl minus, because that's the most stable form of chlorine. So these changes have already happened in nature on Earth. And so we often find sodium and chlorine as their ions. Sodium chloride. Salt is a very common substance on Earth. So given this kind of thought experiment that we just did, that if you're in the 7th row, you need to gain 1 electron, and that will give you 8, and that's a full shell. If you're in the 1st row, you need to lose 1 electron, and then you can access the full shell underneath, but that'll give you 1 positive charge. Then we can kind of develop this map based on how many valence electrons each element has. And this tells us what charge each element is going to have, just based on where it is in the periodic table. All of the elements in the alkali column they all have one electron to lose. Losing one electron gives you a +1 charge. So all the elements in column 1A are going to be +1 ions. All of the elements in column 2A, those are the alkaline earth metals. Remember, they have 2 valence electrons. So if they want to get a full shell, they have to lose 2 electrons. So losing 2 electrons gives you a 2+ charge. So all the elements in the second family have a 2+ charge. Then we skip the transition metals and we go to the 3A, and notice that the elements in family 3A have a 3+ charge, because if they have 3 valence electrons, they have to lose 1, 2, 3, which would give them a 3+ charge. Now when we get to an element that has 4 valence electrons, those are the elements in column 4A. 8 is the magic number here. So far we've said that if you have more than 4, you would probably gain electrons to get to 8. If you have less than 4, you would lose electrons to get to 8. So what I mean by that is, remember the elements in column 1 have 1 electron. They could either lose 1 or gain 7. Those are the ways that they get to 8. If you have 2 electrons, you could either lose 2 or gain 6. It's easier to lose 2 than gain 6. If you have 3 electrons, you could either lose 3 or gain 5. It's easier to lose 3 than gain 5. If you have 4 electrons, it's pretty much the same to either gain 4 or lose 4. You're right in the middle. But then let's go to column 5A. If you have 5 electrons, it's easier to gain 3 more than it is to lose all 5 of them. So if we're trying to get to 8, once we pass elements that have 4 electrons, it gets easier to gain them than it does to lose them. So having all the elements in row 5 are going to gain electrons, 3 of them, and then we'll get to 8. All of the elements in row 6 or in column 6 are going to gain 2 because they already have 6 and they need 2 more to get to 8. All of the elements in family 7A are going to gain 1 because they already have 7 and they need 1 more. And all of the elements in 8A aren't going to gain any because they already have 8. So notice that when we're adding the electrons together, we have 5A plus 3 minus, that's 5 plus the 3 it gains gives us 8. Or 6 plus the 2 that oxygen gains gives us 8. Or 7A plus the 1 minus that fluorine gets gives 8. So that's another reason why metals and nonmetals are different. Notice that zigzag line that separates the metals from the nonmetals? Well, notice here that really the reason for that behavior is because of whether they're gaining electrons or losing electrons. If they have more than 4 electrons, they're going to gain electrons, which means that they pull electrons toward themselves. Whereas if they have less than 4 electrons, they're going to lose electrons, which means that they want to push electrons away from themselves. That's really one of the biggest differences between metals and nonmetals. Do they want to gain electrons or do they want to lose electrons? All elements are trying to get a full shell. They'll either gain to fill up their shell if it's easier, or they'll lose to get access to a full shell underneath, if that's easier. Things that lose are metals. Metals lose electrons to become positive, to become cations. Non-metals gain electrons to become negative, to become anions. And that zigzag line in the middle separates the metals from the non-metals.